Now that we've seen how to fit a structural equation model using the CALIS procedure in SAS, we're ready to look at how to test hypotheses about SEM models. We'll do this in the context of the confirmatory factor analysis example that we started looking at in the previous lecture video. The goal of our hypothesis testing will be to see if the confirmatory factor analysis model can be simplified without significantly compromising or degrading its explanatory or predictive ability. This is a common goal in much of structural equation modeling. This goal is based on the principle of parsimony, a heuristic principle that suggests selecting the simplest hypothesis or model possible from among those having equivalent explanatory power or predictive accuracy. One quote in this direction comes from Albert Einstein. He said, "It can scarcely be denied that the supreme goal of all theory is to make the irreducible basic elements as simple and as few as possible, without having to surrender the adequate representation of a single datum of experience." He's also quoted as saying, "Everything should be kept as simple as possible, but no simpler." Like I said, this is often attributed to Einstein, but its authenticity is questionable. But I do like the simplicity of this statement. It really gets the point across. But I would change it in just one way. This is what I would say. Everything should be kept as simple as is reasonable, but no simpler. So with that in mind, let's take a look at what we're going to be covering in this lecture video. We'll first review the fitted initial confirmatory factor analysis model. Then we're going to define tau equivalence. Once we've done that, we're going to test a sequence of hypotheses. The purpose of these hypothesis tests is going to be see whether it's reasonable to simplify the model in various ways. So let's take a look. So let's review the initial model that we fit using SAS-Proc CALIS in the previous lecture video. So here is the path diagram for this confirmatory factor analysis model. You can see that we have our three latent constructs, F1, F2, and F3. F1 represents a student's ability, F2 represents their achievement motivation, and F3 represents their aspiration. V1 through V8 are the various indicators that are used to assess the factors. Now, in the initial model, we see that we have 8 observed manifest variables. This is denoted by P. The number of model parameters, which is denoted by Q, is equal to 19. That is equal to the number of asterisks in that path diagram on the previous slide. The model degrees of freedom is therefore P times P plus 1 all over 2 minus Q, and so that is 36 minus 19, or 17. And then finally, when we fit the model, we found that the model chi-square value was 20.5813. So here is the full specification for the initial modeling run. This is done in Proc CALIS, and you'll remember that we're using the LIN-EQS modeling language within Proc CALIS. So here's some output from this initial modeling run. We see here the first part of the fit summary table, and we see here that this analysis is based on 250 observations. There are 8 manifest variables, and there are 19 parameters that need to be estimated in order to fit this model. There are 17 degrees of freedom associated with this model, and this agrees with the number that we calculated by hand. Note also that the chi-square value for this model is 20.5813. We're going to be using this very shortly in testing hypotheses about this model. So here's the path diagram for the initial model. Now first, note the double-sided arrows attached to each manifest variable in this diagram. Recall that double-sided arrows represent covariances. Recall also that the covariance of a random variable with itself is equal to its variance. And so these double-sided arrows represent the variances of the manifest variable error terms. Note that this path diagram does not have double-sided arrows representing covariances between pairs of factors. Even though the double-sided arrows are not displayed in this diagram, the covariances have been estimated, and in fact in the previous lecture video we saw what those values were. Now in the previous lecture video I also said that we would show how to add the double-sided arrows with the covariance values in a subsequent lecture, and we're going to do that in this lecture. In fact, here's the code how to do it. So to the path diagram statement, we include the XOG keyword, and this is going to instruct CALIS to display the double-sided arrows for the covariances between the exogenous latent constructs and also to include their estimated values. And so here's the resulting path diagram. Because we use the XOG keyword, two-sided arrows have been included in this path diagram for the covariances between our latent constructs. You can also see the estimated values of those covariances. Okay, now let's look at testing the assumption of tau equivalence of the ability indicators. So let's first answer the question, what is tau equivalence? Well, tau equivalence is the equality of a factor's indicator loadings. Now we're going to be testing the assumption of tau equivalence of the ability indicators. Recall that F1 is the ability factor, and lambda 1, lambda 2, and lambda 3 are the loadings on the paths to the manifest variables that are impacted by F1. Now if the loadings are tau equivalent, then that would mean that they are all equal. And so we could express that this way. So each of those loadings would be equal to lambda 1. Now because they have the same value, they only need to be estimated once. And so I've removed the asterisks on the second and third loadings. I only have an asterisk on the first one. And so in order to test this assumption, the hypotheses to be tested are as follows. The null hypothesis is that lambda 1, lambda 2, and lambda 3 are all equal to each other, against the alternative hypothesis that at least one of them is different than the rest. And I'm going to express that alternative hypothesis this way: lambda 1 not equal to lambda 2 not equal to lambda 3. And I just want to say that that does not mean that they're all different. For example, you could have lambda 1 equal to lambda 2, but lambda 3 being different than the rest, and that would satisfy the alternative hypothesis. But this is just a convenient shorthand way to express the opposite of the null. And so we have our hypotheses to be tested. The model constraint is going to be lambda 1 equal lambda 2 and lambda 3. And so in order to test this hypothesis, we need to fit a model that imposes that constraint. The number of observed manifest variables is still 8. However, the number of model parameters that need to be estimated has been decreased by 2. And so in this case, Q is equal to 17. And so from this, the model degrees of freedom, which again is equal to P times P plus 1 all over 2, minus Q, that turns out to be 19. So there are 19 degrees of freedom associated with this model. Now it turns out that the fitted chi-square value for this model is 25.7416. So let's see how to fit this model in SAS CALIS. So here's the code for this model. Now the one difference between this model and the SAS code for the initial model is that we need to impose the constraint in the hypothesis. All right? And so we see here that we have two constraints that we need to impose. The first constraint here is that lambda 2 is equal to lambda 1. And we impose that constraint by changing L2, which was the coefficient on F1 in the second equation, to L1. Likewise, we change L3 in the third equation to L1, and so that imposes those constraints on the model. We can then run the model and check the results. So again, looking at the fit summary table, we see that we have 250 observations upon which this analysis is based. The number of variables is still 8, but the number of parameters to be estimated is 17. So this gives us an indication that we have indeed specified the model correctly. The chi-square value for this model is 25.7416, and there are 19 degrees of freedom associated with the model. So that also tells us that we have specified this model correctly to CALIS. And finally, check out the p-value associated with this chi-square statistic. We see that it's 0.1376, which is not significant even at the 0.1 level. And so that gives us an idea that the model is not ill-fitting. Now we also want to calculate the p-value for this test. And so here is a data step in which I have hand entered the value for the chi-square test statistic for the full model, which was the initial model, as well as the chi-square statistic for the reduced model, which is this model. I've also input by hand the degrees of freedom associated with the full model, which was 17, and the degrees of freedom associated with the reduced model, which we've seen here, is 19. Now, these values could have been obtained programmatically, but that would take more code and it would be less obvious what's going on. And so just to keep it simple, and for the purposes of this lecture video, and also for your own use, I've opted to look at the output and then copy and paste those values into this data step. And so then once we've done that, I've got the rest of the code there that calculates the critical point for the test as well as the p-value for the test. And then in the print statement below that, I print out those values so that we can look at them. So here are the values for the critical point, the p-value. We can also see the value of the test statistic, which is labeled chi-square change. And so we can see here that the critical point for this test is 5.99146, and that's for a 0.05 level test. And the p-value for the test is equal to 0.075763. So again, we have our hypotheses to be tested. We have the change in the model chi-square values. So the chi-square value for the reduced model minus the chi-square value for the full model, 25.7416 minus 20.5813, and that change in the chi-square value is 5.1603, and this is the test statistic for this hypothesis test. The change in the model degrees of freedom is equal to the difference between the degrees of freedom associated with the reduced model, the current model that we're looking at, and the degrees of freedom for the full model, which in this case is the initial model that we fit in the last lecture video. And so 19 minus 17, or 2 degrees of freedom. So this test has 2 degrees of freedom associated with it. And let me just say that that 2 degrees of freedom corresponds to the number of constraints that are imposed on the model by the null hypothesis. The critical point is the upper alpha percentage point of the chi-square distribution with 2 degrees of freedom. And so if we're using a 0.05 level of significance, that critical point would be 5.991. Now, if we're using the test statistic and critical point method to determine whether to reject the null hypothesis or not, then recall that we would reject the null hypothesis if the test statistic is greater than the critical point. But since 5.1603 is not greater than the critical point, which is 5.991, we see that we would fail to reject the null hypothesis using the test statistic and critical point method. Now, we could also use the p-value method. And again, the p-value for this test is 0.075763. Now you'll recall that the p-value method says to reject the null hypothesis if the p-value is less than or equal to the significance level used for the test. And so if we're performing this test at the 0.05 level of significance, which we are in this case, then we would reject the null hypothesis if and only if the p-value is less than or equal to 0.05. But that's certainly not the case here. And so because of this, we can conclude that there is insufficient evidence at the 0.05 level of significance to conclude that the ability indicators are not tau equivalent. The reduced model incorporating tau equivalence of the ability indicators will therefore be retained and become the model of comparison for the next model. So here's a path diagram showing the simplification provided by the tau equivalence of the ability indicators. Now, let me just say that we have not proven that the ability indicators are tau equivalent. Again, what we're trying to do is to see if it's reasonable to make that assumption and then give the data an opportunity to convince us that it's not reasonable. And in this case, there is not sufficient evidence in the data to convince us that tau equivalence of the ability indicators is not reasonable. And so we're going to proceed under that assumption. Next, let's look at testing the assumption of tau equivalence of the motivation indicators. And so here again is the path diagram for this confirmatory factor analysis model, and F2 is the achievement motivation factor. V4, V5, and V6 are the indicators of achievement motivation, and lambda 4, lambda 5, and lambda 6 are the loadings on those manifest variables. Now, if the motivation indicators are tau equivalent, that would mean that lambda 4, lambda 5, and lambda 6 are all equal. And so then we could change the labeling and label them all as lambda 4. And so the hypotheses to be tested are this. The null hypothesis is that lambda 4, lambda 5, and lambda 6 are all equal, against the alternative hypothesis that at least one of those lambdas is different than the others. And so we have our hypotheses to be tested. In order to perform this test, we have to impose the constraints in the null hypothesis on the model. And so the model constraint would be that lambda 4, lambda 5, and lambda 6 are all equal. The number of observed variables in the model is still 8. But now the number of parameters, again, has been decreased by 2 because we're assuming here, or we're imposing the constraint, that lambda 5 and lambda 6 are both equal to lambda 4. And so the number of model parameters has decreased by 2 from 17 to 15. And so the model degrees of freedom is now equal to 21. Now, once we fit this, we're going to find that the chi-square value for this model is 28.5577. And we compare this to the chi-square value for the previous model, which we have accepted because we did not reject that null hypothesis. Now, how do we fit this model? Well, we need to impose the constraint that lambda 4, lambda 5, and lambda 6 are all equal. And so here is the code for this modeling run. And you can see here that in order to impose the constraints, we have to change two things. We change lambda 5, or L5 in this case, in the equation for V5. We change that from L5 to L4. And then in the equation for V6, we change L6 to L4. And so that imposes the constraints of the null hypothesis. And again, let me just say that there are two constraints here, and this is going to correspond to the number of degrees of freedom upon which this test is based. And so looking at the output from this modeling run, we see that the number of observations upon which the model is fit is 250. We have 8 manifest variables, and there are 15 model parameters to be estimated. The chi-square value for this model is 28.5577. There are 21 model degrees of freedom, and the p-value for this chi-square value is 0.1250. And so looking at that, we can see that there is no evidence of a significant lack of fit by this model. And so that's an indication that the null hypothesis may be acceptable. Now again, we want to calculate the p-value for this test. And so here is the code to do that. And then when we run that section of the code, we see that the p-value for this test is 0.24462. And so looking at the results for this hypothesis test, we see that the change in the model chi-square value is equal to the chi-square value of the reduced model, which is the current model, so 28.5577, minus the chi-square value for the full model, which now is the previous model that we accepted in the previous run, and that is 25.7416. The difference is the change in the model chi-square, and this is the test statistic for this hypothesis test. Again, the change in the model degrees of freedom is equal to the difference between the degrees of freedom for the reduced model, which is the current model, and so we have 21 degrees of freedom for this model, minus the degrees of freedom for the full model, which is the previous model that we accepted, and so that has 19 degrees of freedom. And so the change in the model degrees of freedom, which is the number of degrees of freedom associated with this test, is 2. And again, that's equal to the number of constraints imposed on the model by the null hypothesis. The critical point at the 0.05 level of significance is the upper alpha percentage point of the chi-square distribution with 2 degrees of freedom where alpha is equal to 0.05. And so that critical point is equal to 5.991. The p-value in this case is 0.24462, and that's not going to be less than any significance level that we would ever use, and in particular, it's not less than or equal to 0.05. And so again, we can see that in this case there is insufficient evidence at the 0.05 level of significance to conclude that the motivation indicators are not tau equivalent. And so the reduced model that incorporates tau equivalence of the motivation indicators will be retained and become the model of comparison for the next model. So we've been able to successfully simplify the model in this case because there is insufficient data or insufficient evidence in the data that would indicate to us that this simplification is unreasonable. And so here is a path diagram showing the tau equivalence of the motivation indicators. Next, let's look at testing the assumption of tau equivalence of the aspiration indicators. And so F3 is the latent construct representing aspiration. V7 and V8 are the manifest variables impacted by F3, and lambda 7 and lambda 8 are the corresponding loadings. And so if the aspiration indicators are tau equivalent, that means that they are equal, and so we could change the labeling. So for example, they are both lambda 7. So to test this assumption, the hypotheses that need to be tested are as follows. The null hypothesis is that lambda 7 is equal to lambda 8, with the alternative hypothesis being the opposite of that statement. And so we have our hypotheses to be tested. In order to test this hypothesis, we have to fit a model that imposes the constraints of that null hypothesis, and that constraint would be that lambda 7 is equal to lambda 8. We still have 8 manifest variables, but now we have 14 model parameters that need to be estimated. If lambda 7 is equal to lambda 8, then we are reducing the number of parameters by 1. And so we've reduced the number of model parameters from 15 in the previous model to 14 in this model. The model degrees of freedom, p times p plus 1 over 2 minus q, is equal to 36 minus 14, or 22. And so by decreasing the number of model parameters by 1, we've increased the model degrees of freedom by 1, from 21 to 22. When we fit this in Proc CALIS, we're going to find that the chi-square value associated with this model is 28.5979. And so here is the Proc CALIS code for fitting this particular model. And note that the constraint is imposed by changing L8 in the equation for V8 to L7. And so that imposes the constraints in the null hypothesis that says that L7 is equal to L8. Looking at the fit summary table, we see that we've got 250 observations upon which the model is based. The number of variables is 8, and again, the number of parameters is 14. In addition, the number of degrees of freedom associated with this model is 22, and so putting that information together, we can be fairly certain here that we have fit or specified the model correctly. The chi-square value for this model is 28.5979. And again, looking at the p-value for that chi-square statistic, we don't see any significant evidence of lack of fit. Here's the code to calculate the p-value for the test. Same as before. The only difference is we've got different values that we've entered into the data step for the chi-square value for the full model, the chi-square value for the reduced model, as well as the degrees of freedom. And so here's the output from that print statement, and we can see here that the p-value for the test is 0.84109. And so looking at the results for this test, we see that the change in the model chi-square values is 0.0402, which is quite small. That, again, is the test statistic for this hypothesis test. The change in the model degrees of freedom, which is the number of degrees of freedom for this test, is equal to 22 minus 21, or 1. And again, the number of degrees of freedom associated with this test or corresponds to the number of constraints imposed on the model by the null hypothesis. And we imposed one constraint, and so we know from that as well that this hypothesis test is based on 1 degree of freedom. The critical point, using a 0.05 level of significance, will be the upper fifth percentage point of the chi-square distribution with 1 degree of freedom, and that turns out to be 3.841. Now, since the test statistic, 0.0402, is not greater than 3.841, we know that we're going to fail to reject the null hypothesis at the 0.05 level of significance. But we could just as easily have used the p-value method, the p-value being 0.84109. And since that is not less than or equal to 0.05, we also see, based on this, that we would fail to reject the null hypothesis. And so we can conclude that there is insufficient evidence at the 0.05 level of significance to conclude that the aspiration indicators are not tau equivalent. The reduced model incorporating tau equivalence of the aspiration indicators will be retained and become the model of comparison for the next model. So here's the path diagram showing tau equivalence of the aspiration indicators. Again, F3 is the aspiration factor. V7 and V8 are the indicators impacted by F3. And you can see here that we've changed lambda 8, the loading on the path to V8, to lambda 7 to represent that tau equivalence. And because it's the same as the loading on the path to V7, we only need to estimate it once, and so I've taken the asterisk off of that last loading. Next, let's look at testing the assumption of equality of the covariances between factors. So here is the path diagram that we have so far. You can see that we've implemented, or we have represented here, the tau equivalence of all three of the latent constructs. The tau equivalence of the ability indicators, the tau equivalence of the achievement motivation indicators, as well as the tau equivalence of the aspiration indicators. Here we have the covariances between the various factors. And so we're going to test the null hypothesis that those covariances are all equal. So the hypotheses to be tested here are as follows. The null hypothesis being that cap phi 1,2 is equal to phi 1,3 is equal to phi 2,3. So all three of those covariances are the same. Against the alternative hypothesis that at least one of those covariances is different than the rest. And so we have our hypotheses to be tested. And in order to test this hypothesis, we have to impose the constraints of the null hypothesis on the model. And so the model constraints to be imposed are that these three covariances are equal. The number of observed variables is still 8. But now we've reduced the number of parameters by 2, and so the number of model parameters to be estimated in this case is going to be 12. The model degrees of freedom are therefore 24. And when we fit this model, we're going to see that the chi-square value for the model is quite large, 69.6521. Now here is the CALIS code for this modeling run. And you can see here that what we have to do to impose the constraints in the null hypothesis on the model is to change the name that we have assigned to the covariance of F1 and F3 from cov underscore F1 underscore F3 to the same as the name that we have for the covariance of F1 and F2, namely cov underscore F1 underscore F2. And we have to do the same thing for the name of the covariance between F2 and F3. We change it from cov F2 F3 to cov F1 F2. And so by imposing or by changing these two names of the covariances that we've assigned, we have imposed the constraints of this null hypothesis. Looking at the fit summary table, we see that we have 250 observations, we have 8 variables, and we have 12 parameters that need to be estimated in order to fit this model. There are 24 degrees of freedom associated with this model. The chi-square value for this model is 69.6521. Again, that's quite large, especially in comparison with the number of degrees of freedom associated with the model, which is 24. And we also see that in this case, the p-value for that chi-square value is quite small. So that's telling us that there seems to be a problem with lack of fit. Here's the code to calculate the p-value for the test. And here's the p-value itself. We see that it is 1.2167 times 10 to the minus 9th. So it's very, very, very small. We have a very small p-value here, and so we can tell that this is going to be a very significant result. So let's look at the results of this test. Again, we have the hypotheses being tested. The null hypothesis being that the 3 covariances between the latent constructs are all equal to 0, against the alternative hypothesis that at least one of those covariances is different than the rest. The change in the model chi-square value is 41.0542. This is the test statistic for this test. The number of degrees of freedom associated with this test is the change in the model degrees of freedom, 24 minus 22, which is 2, and this is also equal to the number of constraints imposed on the model by the null hypothesis. Now at the 0.05 level of significance, the critical point for the test is the upper fifth percentage point of the chi-square distribution with 2 degrees of freedom, and this is equal to 5.991. And because 41.0542 is greater than 5.991, we can see that we are going to reject this null hypothesis. We could also use the p-value method, and since 1.2167 times 10 to the minus ninth is less than or equal to 0.05, the rejection criteria have been satisfied, and so we can see that we would reject the null hypothesis. So the conclusion would be that there is sufficient evidence at the 0.05 level of significance to conclude that the covariances between the factors are not equal. The reduced model, incorporating equality of the covariances between factors, will in this case not be retained. Model 4, the previous model, remains the comparator for the next model. So here we have the path diagram that retains the distinct covariances between the factors. Now, let's test the assumption that the covariances between F1 and F2 and between F2 and F3 are equal. And so this is a little bit more specific than the previous test. Here what we're doing is testing that cap phi 1,2 is equal to cap phi 2,3. And so that's going to be the test that we're going to perform in this particular situation. The null hypothesis being that phi 1,2 is equal to phi 2,3 against the alternative hypothesis that phi 1,2 is not equal to phi 2,3. And so we have our hypotheses to be tested. In order to perform this test, we have to impose the assumption of the null hypothesis on the model itself. The number of observed variables is equal to 8. The number of model parameters in this case is 13. And so we have 23 model degrees of freedom. We're going to see that the chi-square value for this fitted model is equal to 28.9109. Now here's the SAS code, CALIS, to fit this model. And so we can see here that to impose the constraint in the null hypothesis on the model, we just have to change the labeling of the third covariance name, which was cov F2 F3. We change that to cov F1 F2. Looking at the fit summary table, again, the model is based on 250 observations. There are 8 variables, and we have 13 parameters. And so that corresponds to what we've calculated by hand, and so that gives us some assurance that we've specified the model correctly. We also see that the number of degrees of freedom associated with this model is 23, and so that gives us further assurance that we've specified the model correctly. Now the chi-square value for this model is 28.9109, and we can see here that the p-value associated with that chi-square value is not significant at any significance level that we would typically use. And so we don't see any evidence of lack of fit in this model. We have the data step here to calculate the p-value for the test. And then printing out that data set, we see that the p-value for the test is 0.57585. And so here we have the results of the test. The change in the model chi-square value is 0.3130. The change in the model degrees of freedom is 23 minus 22, or 1 degree of freedom. and that corresponds to the one constraint that would be imposed on the model from the null hypothesis. The critical point for the test at the 0.05 level is the upper fifth percentage point of the chi-square distribution with 1 degree of freedom, and that value is 3.841. Since 0.3130, the test statistic, is not greater than 3.841, we can see that we would fail to reject the null hypothesis. The p-value for the test is 0.57585. That is not less than or equal to 0.05. So again, we would see from that standpoint that we would not reject the null hypothesis. And so the conclusion is that there is insufficient evidence at the 0.05 level of significance to conclude that the covariance between factors f1 and f2 and the covariance between factors f2 and f3 are different. The reduced model incorporating equality of these two covariances will therefore be retained and become the model of comparison for the next model. And here is a path diagram showing this simplification. Next, let's test the assumption that the variances of all error terms are equal. So here's the path diagram, and I've outlined here the various error terms in the model, E1 through E8, and notice that each one has associated with it an asterisk. And that tells us that the variances of those error terms all need to be estimated. But if the variances are equal, we only need a variance on, let's say, the first error term, and so this is what that corresponding path diagram would look like. So here are the hypotheses to be tested in this situation. The null hypothesis is that the variances of the 8 error terms, E1 through E8, are the same. The alternative hypothesis is that at least one of those variances is different than the others. So here we have the hypotheses to be tested. The model constraint is obtained by setting all of those variances equal to the same thing. The number of observed variables is going to be equal to 8. The number of model parameters has now been reduced to 6. And so the number of model degrees of freedom is equal to 30. Now when we fit this model, we're going to find that the chi-square value for the model is 58.6160. Here's the code to fit this model. And we can see here that in order to impose the constraints in the null hypothesis on the model, all we have to do is to change the labeling of the names of the variances that we have specified in the model to var E1. So all of them are going to be changed to var E1. And then when we run this, we see the following information in the fit summary table. Again, we've got 250 observations upon which the model is based. We've got 8 manifest variables, but now we have 6 parameters to be estimated, and that corresponds to the value that we calculated by hand. We have 30 model degrees of freedom. The chi-square value for this model is 58.6160, and again, looking at that p-value for the chi-square value, we see that it's significant. And so that indicates to us that we have lack of fit. We have here the code to compute and print out the p-value for the test. And so we see that the p-value is 0.0001-07544. And so the p-value is quite small. And so here we have the results of this test. The change in the model chi-square is 29.7051. The change in the model degrees of freedom is 30 minus 23, or 7. The critical point for the test at the 0.05 level of significance is the upper fifth percentage point of the chi-square distribution with 7 degrees of freedom, and that value is 14.067. Since 29.7051 is greater than 14.067, we can see that we would be rejecting the null hypothesis. Equivalently, because the p-value, 0.0001, 0.7544 is less than or equal to 0.05, we can see that we would be rejecting the null hypothesis. There is sufficient evidence at the 0.05 level of significance to conclude that the variances of the error terms are not equal. The reduced model incorporating equality of these 8 variances will therefore not be retained. And so here's a path diagram showing that we are retaining the distinct error variances. And this is shown by the fact that we have asterisks on all of the error terms. Next, let's test the assumption that the variances of the error terms of each factor's indicators are equal. Under this assumption, the variances of E1, E2, and E3 are going to be equal. The variances of E4, E5, and E6 will be equal. And finally, the variances of E7 and E8 will be equal. And so the path diagram would change in this way. We see that the asterisks on E2 and E3 have disappeared, as have the asterisks on E5 and E6, and the asterisk on E8. And so here are the hypotheses to be tested. The null hypothesis, that the variance of E1, the variance of E2, and the variance of E3 are equal, and the variance of E4, the variance of E5, and the variance of E6 are equal, and the variance of E7 and the variance of E8 are equal. The alternative hypothesis would be that at least one of the variances of E1, E2, and E3 are different from each other, or at least one of the variances of E4, E5, and E6 are different from each other, or the variance of E7 and E8 are different. And so the model constraints that we impose in order to test this hypothesis are the following. The variance of E1 and the variance of E2 and the variance of E3 are equal, and the variance of E4, the variance of E5, and the variance of E6 must be equal, and finally the variance of E7 and the variance of E8 are equal. The number of observed variables is still going to be 8. The number of model parameters, in this case, will be 8. And so we're going to have 28 model degrees of freedom. We're going to find that the chi-square value associated with this model is 32.8281. So here's the proc-CALIS code to fit this model. And we see that in order to impose the constraints in the null hypothesis on the model, all we have to do is change the names that we've assigned to the variances of E2 and E3 to var E1, change the name of the variances on E5 and E6 to var E4, and finally change the label or name of the variance for E8 to var E7. And so we see here that we have 250 observations. We have 8 variables, and we have 8 parameters to be estimated. There are 28 model degrees of freedom, and the chi-square value for this model is 32.8281. Now note also that the p-value associated with that chi-square value is fairly large, 0.2421, and so there's really no indication, at least based on this p-value, that there is lack of fit in this particular model. We have the data step to calculate the p-value and the print statement to print it out. And so we see here that the p-value for the test is 0.56140. And so then looking at the results of this test, the test statistic is 3.9172, the number of degrees of freedom associated with this test is 5. This is equal to the change in the model degrees of freedom, 28 minus 23, but it's also equal to the number of constraints imposed on the model by the null hypothesis. At the 0.05 level of significance, the critical point is the upper fifth percentage point of the chi-square distribution with 5 degrees of freedom, and that value is 11.0705. Now, since 3.9172, the test statistic, is not greater than 11.0705, we can see here that we would not reject the null hypothesis. The p-value for the test is 0.56140, and so if we're using the p-value method, since 0.56140 is not less than or equal to the significance level that we're using, 0.05, we would again see that we would fail to reject that null hypothesis. And so the conclusion is, there is insufficient evidence at the 0.05 level of significance to conclude that for any of the factors, the variances of its indicator error terms are different. The reduced model incorporating equality of each factor's indicator error variances will be retained. And so here is a path diagram showing that we are retaining equality of indicator variances for each factor. And so we've gone through the various hypothesis tests that we wanted to look at, and we've come up with a final model. So let's take a look at that. We see here that we have tau equivalence of the indicators for each of the latent constructs. The loadings on all of the manifest variables coming out of F1 are all equal to lambda 1 in this model. The loadings coming out of F2 on its indicators are all lambda 4, and the loadings emanating from F3 on its factors, or on its indicators, are all lambda 7. We have retained equality of the two covariances, the covariance of F1 and F2, and the covariance of F2 and F3. And we have retained equality of the variances for the indicators for each factor. Here is the path diagram produced by SAS-Proc-CALIS for this final model. We can see that the estimated values of the loadings on V1, V2, and V3 are all equal to 0.55. The estimated values of the loadings for V4, V5, and V6 are all equal to 0.57. And the loadings on V7 and V8 are both equal to 0.62. We can see here that the covariances between F1 and F2, as well as F2 and F3, are both equal to 0.66. We can see here that the variances of the manifest variables V1, V2, and V3, or equivalently the variances of their error terms, are all estimated to be 0.18. The variances of the error terms on V4, V5, and V6 are all estimated to be 0.29. And finally, the variances of the error terms associated with V7 and V8 are both estimated to be 0.21. Now, what about model fit? Well, down in the right-hand corner, we have some model fit indices. And so let's take a look at those and compare them to the criteria that we looked at in a previous lecture video. So we can see here that the model chi-square value, it is a little bit larger than the model degrees of freedom, but not by much. And we can see here that the model chi-square p-value is not significant. So based on that p-value, we're not seeing any significant lack of fit. The AGFI, the Adjusted Goodness of Fit Index, is at or above the midpoint 9s, and that was the criterion that would indicate a reasonably good fit to the data. The CFI, the comparative fit index, is at or above the midpoint 9s, again indicating a reasonably good fit to the data. The RMSEA is less than 0.05, and again, that is the criterion for a good fitting model. And so based on these model fit indices, the model appears to fit the data well. So we've done a lot in this lecture video. We took the initial confirmatory factor analysis model, and we subjected it to a number of hypothesis tests where we were testing various simplifying assumptions. Some of those assumptions we had to reject, but others we were able to retain. And in doing so, we came up with a much simpler model. So that's what I wanted to show you in this lecture video. I'll see you in the next video.